Hi folks, we're going to continue with a short review of what we looked at last class. We were looking at section 2 section 1 lesson 2, free body diagrams and combining forces. So last class we introduced the idea of what a free body diagram was, and what a free body diagram, the purpose is that it will show all the forces acting on an object. And we began the class with examining the person over here in this picture. In most cases, all forces point outwards from the object and are seen to act from the center of the object. So let's go through the forces that would be acting on the person here. So we look at the man here, and we'll consider from the center of the object. First, you have a force of gravity pulling you down. Now, since the person is not sinking into the pavement, there must be a normal force resisting that. So that's what we call the force going against gravity. It's called the normal force. And it's represented by F and this lowercase n, subscript n. We also have the person who's pushing forward, but there's a certain amount of friction associated with the tires and the mass of the car, and even the type of pavement. The friction on pavement will be greater than it would be on ice. So the frictional force is resisting the movement of the person and force of friction. So that's summarized here in a neat little diagram. So we have the force applied, that's the person applying the force. We have a frictional force resisting it, force of gravity pulling you down, and a normal force. So let's consider this other example here. Here we have a boat with all the forces showing on it. The first force here, as you see, is the force of the wind pushing on the sails. We have gravity, which is pulling the boat into the water. But we also have, the buoyancy force pushing upward. Now that will be our normal force, but in this case it's buoyancy due to the qualities of the boat and the water. And we have drag, and drag is the force that acts between the boat and water. This is trying to prevent the movement. If you want to think about drag forces in terms of water, sorry guys. If you want to think about drag forces in terms of water, think about Olympic swimmers. Many of them wear these bodysuits, silicone bodysuits that prevent them from building up a lot of friction in water, lets them go through easier. So drag does have an effect on even small objects like people, and even with large objects like boats. And for some of you who may have been around fishing boats, you know that every so often they're taken out of the water in the spring of the year, and the bottom of the boat is scraped to remove any algae or barnacles or anything building up, because that increases drag force. So if you see the word drag here, when we're dealing with forces, it's also going to refer to frictional forces. Alright, so free body diagram representing an object being pulled across the table at a constant speed. So we have a force here pulling an object across the table. There will be a frictional force. There's a force of gravity and a normal force. The net force of an object is sum of all the forces acting on an object. So what you have to consider with net force, and we'll begin this soon, next slide or two, is that you look at forces in opposite directions. So those acting west-east, those acting north-south. And we can add those arithmetically. And you'll see that in a second. And we can do the same with the force of gravity and normal force. Now for most objects, if they're not moving up and down, the force of gravity and normal force would be equal. So if the object's not sinking or moving down or rising up, the normal force is equal to the force of gravity. And if an object's moving at a constant speed, then the applied force is just enough to overcome friction. So if you're pushing on a car and the car's in neutral and you can't get the car to move, it means that your applied force is less than your force of friction. So if you can't get a car to move, then your force applied will be less than frictional force. But if you get the car to move at a constant speed, then the force applied would have to be equal to the force of friction. You're applying just enough speed to get the car to move at a constant speed. Now if you're getting the car to speed up, well, you're applying more force than is needed. So your force applied is greater than the force of friction. So in this case here, the car will be accelerating. Here you would have a constant speed. And in this case, the object doesn't move. Okay, so in the first part of the video there, I don't want to go too long in the video, and in the next one we'll begin some examples.